I would like to talk about how we get the derivatives of the trigonomic functions. First thing I want to deal with is sine and cosine, and I have three graphs here. The graph in red is the graph of f of x equals the sine of x. The graph in G is equal to the cosine of x, and H is the graph of negative sine of x, and we'll talk about green last. So, getting the derivative of sine using pure limit theory is a little bit beyond the scope of this course, so we're going to use a graphical technique to show you how we get the derivative of the sine of x. So again, it's the red function, and I'm going to do so by drawing some tangent lines. I know at pi over 2, I have a tangent line whose slope is 0, which means if I want to graph the derivative of sine of x, I would go to pi over 2, comma 0, and plop a point right there. So also notice on the red graph of sine of x at 3 pi over 2, if I drew the tangent, the slope of that tangent would also be 0. So if I wanted to plot a point on the derivative, I would go to 3 pi over 2, comma 0, and drop a point. There it is. Now, notice between the first max and top of the curve and the bottom of the curve where my derivatives go to 0, halfway in between my function is going down at the most. I'm actually not going to plot a point there, but I just want to show you this location. Now, so my tangent line will have a slope that is negative. Now, I could fairly easily estimate this value using a limit at the 1 point, using my average rate of change, and if I did, I would find that the slope of the tangent line drawn here would be negative 1. And again, I would have to make a little table, limit theory, average rate of change. So if I was to plot this point, pi, comma, negative 1, I would plot it right there. Interesting. At 2 pi, if I drew a tangent, again, on the function sine, and did the same thing, calculated the average rate of change as a limit going to 0, I would find that the slope of the tangent line there is 1. And again, to graph my derivative, I would plot the point 2 pi, comma 1. You might have noticed something. Everywhere that I did this, I landed on the cosine of x. And that is my first property, that the derivative of the sine of x is in fact the cosine of x. Now, we're going to do the exact same technique for cosine. And again, this is not a proof, this is just an illustration. So cosine is the function in blue. I'm going to draw tangent lines. First tangent line at pi equals 0. I'm sorry, at x equals 0, x equals pi, and x equals 2 pi. And I know the slope of those tangents are all 0. So to graph the derivative of cosine, I would start off with those x values, and each one of them would have an output at 0. And I will do that. 0, 0, plot that point. Pi, 0, and 2 pi, 0. Now, notice, in between my first tangent line and the second tangent line, my function cosine is going down, which means all of its derivative values will be negative, with the steepest being here at pi over 2. And if I was to take the limit of the average rate of change around pi over 2, I would find that the slope of that tangent is negative 1. So I will now plot the point pi over 2, negative 1. And again, using the same logic, at 3 pi over 2, I could calculate the average rate of change, Chapter 2, Section 2, and the average rate of change as we approach 3 pi over 2 would give me a slope of that tangent line at 1. And if I was to plot that point, 3 pi over 2, comma 1, I would end up here. And what you notice is that the green graph is located every single place that I was plotting my points for my derivative, or the tangents, slopes at those x values, which leads me to the derivative of cosine. The derivative of cosine of x is negative sine of x. Again, this is not a proof, but an example showing that it is consistent. Now,